Okay, hi everybody. We're going to start this video with the learning check. This is the last learning check of chapter 12. So we had just talked about unit cells, simple cubic, body-centered, and face-centered. This is one of the types of questions you can see that's about the unit cell concept. So this question says copper has an atomic radius of 128 picometers. Calculate and compare the densities of two hypothetical forms of copper. One is simple cubic unit cells and the other of face-centered cubic. So let's see, we've got radius already, we have the R value, and we're looking for density. Remember, density is mass over volume. And the question is about the densities of two forms. We're looking at two different unit cells. So we're looking for the mass of copper in a unit cell and the volume of that unit cell. And then we could calculate the densities. To find mass, well, we're going to start with A, which is simple cubic. To find the mass of copper in a unit cell, we need to know how many atoms are present and then the mass of those atoms. Well, a simple unit cell has one atom per unit cell. And that info is on the slides where we just gave an overview of those three different types of unit cells that we're covering in our chapter. So if we have one atom per unit cell, we can eventually get to the mass of that one atom or of the one unit cell by converting atoms to moles and then moles to grams. So we can convert atoms to moles using Avogadro's number. 6.022 times 10 to the 23rd atoms are present in 1 mole of atoms. And then 1 mole of copper, looking at the periodic table, is 63.546 grams. So with this calculation, we cancel atoms, we cancel mole, we're left with grams per unit cell. And if you plug all this into your calculator, we have 1.055 times 10 to the negative 22nd grams of copper per unit cell. So that's how we get the mass of a certain unit cell. I'll just write this as mass here. Next will be volume. The volume of a cube is the length of an edge cubed. We know that for simple cubic, the length of the edge is 2r. Now, while I explain it, I'm going to do a unit conversion for r first. You could convert at the end, but usually density is in grams per milliliter, which is equal to grams per centimeter cubed. A milliliter is equal to a centimeter cubed. But we're given radius in picometers, so I'm going to first convert from picometers to centimeters. And then I'm going to convert just using what we ask students to memorize in Gen Chem 1. So a picometer is 10 to the negative 12 meters. So that will convert picometer to meter. And then a centimeter, which is what we're looking for, is 10 to the negative 2 meters. So those are the conversions that we learn in Gen Chem 1. You could go straight from picometers to centimeters if you want to look up or just figure out that conversion. But just using what we asked students to remember in Gen Chem 1, that's how we can do this conversion. Cancel out picometers and meters, and we're left with centimeters. This is 1.28 times 10 to the negative 8 centimeters. Okay, so that's radius. Length, or let's write edge length. For a simple unit cell is 2r, which is, of course, 2 times the radius that we just calculated in centimeters. Which is 2.56 times 10 to the negative 8 centimeters. Now that we know edge length, we can find volume, which is edge length cubed, 2.56 times 10 to the negative 8 centimeters cubed. This is 1.68 times 10 to the negative 23 centimeters cubed. So that is the volume. I'm going to erase volume up there so we don't get confused. Okay, so that's our volume. The last thing, so step 1 was to find mass. 2 was all for volume, converting radius to centimeters, finding the edge length, and then finding the volume. 3 is calculating density, which again is mass over volume. Mass being 1.055 times 10 to the negative 22 grams, and volume we just calculated, 1.68 times 10 to the negative 23 centimeters cubed. This is, calculate that, 6.29 grams per centimeter cubed. That is the density of copper if it is arranged in simple cubic cells. If it is arranged in a different cubic cell, like face-centered, the density will be different. We have a different mass per unit cell and we'll have a different volume. So we'll move on to that now. I'm going to scroll down here to do part B. Again, step 1 is finding the mass. But remember, part 1 was about simple unit cells. Part B asks about face-centered unit cells. Face-centered unit cells have 4 atoms per unit cell. So when we're finding the mass, we need 4 atoms per 1 unit cell. And then we're doing the same conversions as up here, converting from atoms to moles and then moles to grams. And this is 4.221 times 10 to the negative 22nd grams of copper per unit cell when the unit cell is face-centered. Okay, so that's the mass for face-centered unit cell. Now we need to find the volume. Now we've already converted radius and picometers to centimeters, so we can just go ahead with edge length. For a face-centered cubic cell, the edge length is square root of 8 times r. So this is square root of 8 times 1.28 times 10 to the negative 8 centimeters. Again, we converted to centimeters in the first part, part A. And this is equal to 3.6 times 10 to the negative 8 centimeters. So that is the edge length, face center cubic for copper. Volume, we take that edge length and cube it. 3.6 times 10 to the negative 8 centimeters. All of that gets cubed. This is 4.745. So we'll do 4.75 times 10 to the negative 23 centimeters cubed. So we have found the mass, we have found the volume. Last step is to calculate density. I'll just do it below actually. Where it is mass over volume, it is 4.221 times 10 to the negative 22nd grams divided by 4.75 times 10 to the negative 23 centimeters cubed. If you calculate that, you should get 8.89 or 8.90 grams per centimeter cubed. So that is our final answer here. So as in this example, we knew the radius. We were told face-centered or simple. We could then calculate the mass knowing the number of atoms per unit cell, and the volume knowing the equation for edge length plus the radius. Then we calculate density. One thing we talked about when we looked at the different types of unit cells was that the simple cubic is the least dense. And if you compare the densities here, we're looking at 6.29 grams per centimeter cubed compared to 8.90. So we see that simple cubic is less dense than the face-centered cubic. Okay, we will stop chapter 12 now, and I'm going to go ahead and go to the chapter 13 PowerPoint slides, and we will continue there. So we've talked about liquids, solids, gases. Now we're going to talk about the combination of different substances. Most of the time when we're talking about solids and liquids and gases so far, we're pretty much talking about pure substances, but lots of substances exist as solutions or mixtures of different substances. So that's what this chapter is all about. The image here is showing both the observation of dissolving salt in water, and those particle pictures are showing the difference between pure water and pure salt on the left, and then the mixture of salt and water on the right, where the salt that has dissolved into cations and anions, and water is surrounding those ions. So anyways, let's continue chapter 13, all about solutions. So our chapter outline here, we're going to talk about the solution process. We'll talk about saturated, unsaturated, and supersaturated solutions. If we have a solution, something is dissolved in something else. We can describe the concentration of that solution, so how much of a certain thing is present. So we'll talk about concentration units. Then we'll talk about how properties of solutions are slightly different than the properties of the pure substances. So that's the last two sections of chapter 13. Okay, so 13.1, this is what we'll focus on for this video. The solution process. So we're going to talk about some language for solutions, different types of solutions, and then we'll get to the energetics of the solution process, how to predict what types of solvents are most likely going to dissolve a given solute. We'll talk about what those words are. So first, some language. Solution is a homogeneous mixture of two or more substances. We've talked about mixtures back in Gen Chem 1. Homogeneous mixture means it appears to be one substance. You visually can't see the difference. The solvent is the part of a solution that's typically present in the greatest amount. If you think back to that first slide where we looked at table salt dissolving in water, water would be the solvent. It dissolves the table salt. This also determines the state of a solution. You can have a solution of gases. You can have a solution of solids. You can have a solution of liquids. Whatever the solvent is determines the state of that solution. And then anything else is called a solute. So that is a solution component that is not the solvent. So that would be sodium chloride in the example that we've looked at. And then again, solutions can be gaseous, liquid, or solid. We're going to talk about each of those in this section. But first, a substance's ability to form solutions. This depends on the two factors. The second and third bullet point should be indented a little bit. But the ability of a substance to form solutions depends on its natural tendency towards mixing. One example I like to give here is if you're trying to make a solid solution, let's say you're mixing two different metals together, well, you can't just take a solid gold piece and a solid silver piece and push them together. They're not going to mix. They don't have a natural tendency towards mixing. Now you can adjust that by melting, but the ability of something to form a solution depends on that tendency towards mixing. The other important piece that we'll talk a lot about this chapter is that this depends on intermolecular forces. And we will certainly talk about why intermolecular forces are important here. Next, we're going to talk a little bit about liquid, then about gas solutions, and about solid solutions. And then there's more to cover yet in this section. There's kind of a lot here. So first, liquid solutions. Liquid solvents, so the thing that dissolves solutes, can dissolve other liquids, it can dissolve gases, it can dissolve solids. So I have a few examples here. Just looking at water, if you drink a pop or any carbonated beverage, those are prepared, like pops and just carbonated like juices, those are prepared by dissolving gaseous carbon dioxide in water. So the carbon dioxide is forced into the water. These beverages are mostly water, there's some sugar, there's some other flavors in it, but that carbonation is gaseous carbon dioxide dissolved in the water. That's when you see those bubbles come out, those are carbon dioxide bubbles. That's also why when you leave your pop can open or the bottle open, it ends up becoming flat. All of the CO2 evaporates out of the solution. But when it's capped and closed, those CO2 gaseous molecules are forced to remain in the liquid. Okay, so that's gas dissolved in liquid. An example of liquid in liquid is vodka. That drink is prepared by dissolving liquid ethanol, so a different molecule than water, but dissolving the ethanol in water. And then an example of a salt dissolved in water is just salt water. So you can prepare that by dissolving solid salt in a water cup. A little bit about the salt dissolving process. We've seen this before. This is another visual to describe the dissolving action of water on an ionic solid. So remember, water is polar. It's represented right here. I'll also draw the Lewis structure. The hydrogen to oxygen bond is polar, with partial negative near oxygen, partial positive near the hydrogens. So when an ionic lattice is added to water, the water hydrogens, partial positive hydrogens, are attracted to the anions, the negatively charged ions in the lattice. So they begin to surround the lattice. That's what is being shown over here. They begin to surround the anion, and then eventually the negative ion is surrounded by water molecules. So this is the ion dipole interaction. And then same thing happens if we look at the left side of this image. The negative ends of water, which is really the oxygen, is attracted to the positive ions in solution. Eventually they will surround the ions, and that's what occurs in solution with an ionic compound. Okay, so that was a little bit about liquid solutions. We'll certainly talk more about them. But next we have gaseous solutions. So gaseous solvents can dissolve gases, or they can dissolve other gases that are normally liquids or solids. Hopefully the examples will help clarify that. But in gaseous solutions, each component behaves independently of the others. This was one of the pieces of the ideal gas law, where we'd say if you have a mixture of gases, they behave independently. Here are some examples of gaseous solutions. A great example is air in our atmosphere. Air is a gaseous solution. Molecular nitrogen, N2 gas, is in highest concentration, so that is the solvent. And then it also has molecular oxygen. It has CO2. There are other gases as well, but those are the highest concentration gases. So air is nitrogen gas dissolving other gases. But if you go outside in the summer after it rains, you might notice that the air is really humid. When it's really hot and you feel that humid air, that is air with water molecules, so H2O molecules, that have evaporated from the liquid phase. So it is still H2O, but it is the vapor, it's water vapor, dissolved in the nitrogen atmosphere. Another example is like any scent. The one on this slide is mothballs. If you've smelled mothballs before, they are composed of naphthalene. That is a solid molecule, but that molecule sublimes in air. So it goes from a solid to a gas. When it's in the gas phase, dissolved in the nitrogen atmosphere, we can smell it. So those are a couple examples of gaseous solutions. Next, we've got solid solutions, and then we'll dive deeper into solutions. So solid solutions are difficult to prepare. Mixing atoms or molecules that are solids are difficult because they do not move freely. But there are some examples of solid solutions like metallic alloys. This is a mixture of different metals. You can melt metals down, and we'll talk more about this, but you can melt them down, mix them together, and then when they are cooled again, they solidify into a solid, but they're still a mixture, they're still a solution. Certain compounds are added to plastics to adjust the strength. Some examples are BPA. If you've seen bottles that are like BPA free, that's a chemical that can be added to plastics to adjust the strength. Same thing with phthalates. Those can be added to plastics. Now, there are many others, but those are two that come to mind. Another solid solution would be carbon is added to iron to make steel. So steel is a mixture of carbon and iron. Okay, so that was some background info about different types of solutions. We're going to move into what substances would be soluble in other substances based on the properties of the solute in the solvent. So if we have miscible substances, these are substances that form solutions in all proportions. An example here is acetone and water. So acetone is a really common lab solvent. If you're not already using it in Gen Chem lab, you will definitely use it a lot in organic lab. It's used to clean glassware because it dissolves a lot of different things. And we will actually talk about why. We have another slide all about acetone. But anyways, acetone and water can be mixed in any proportion. It doesn't matter if you have 99% of your mixture is water, 1% is acetone, it'll dissolve. Or if you have 99% acetone, 1% water, they'll also mix. Or if you have 50-50, anywhere in between, those two substances are always miscible. They will always form a solution with each other. The opposite of that would be insoluble substances. These substances, well, this would be used to describe a solute that does not dissolve well in a solvent. We talked about sodium chloride dissolving in water. Sodium chloride would not dissolve in gasoline. If you added salt to gasoline, it would just stay as a solid. It would not separate into its ions. So we would say sodium chloride is insoluble in gasoline. Now we can use properties of molecules, solutes, and solvents to predict if something would be soluble or not. And we use this rule or this phrase, like dissolves like. Essentially what we're looking for is intermolecular forces. Substances that dissolve in each other usually have similar types of intermolecular interactions, intermolecular forces. That's what we're looking for. Examples, water and methanol. So looking at this first one here. Both molecules are polar. Both molecules exhibit hydrogen bonding. Those two substances are miscible. They have the same intermolecular force capability. They're also both polar, so they dissolve. Second example, octane and cyclohexane. Both of these are composed of only carbons and hydrogens. They are both nonpolar. They only exhibit dispersion forces, but they both exhibit the same type of intermolecular force, so they are miscible. They can mix with each other. But if we took one from each of those bullet points, so octane, which is nonpolar, has dispersion forces only, and added it to water, which is polar and has hydrogen bonding interactions, these would not mix. They would form two different layers, and those two layers would not mix together. So these are immiscible or insoluble. The next slide has some images, both particle pictures and observational pictures, like a macro view of what this would look like. So looking at just the left side for now, where I just drew that bracket. The top two molecules, this is octane. You can see the formula here. This is cyclohexane. Each are only made of carbons and hydrogens. They are miscible with each other because they both have dispersion forces. Then on the bottom, we have methanol and water. These both have hydrogen bonding interactions, so they are miscible with each other. But ethanol and water are insoluble, or immiscible with cyclohexane and octane. The picture on the right now, you can see there is octane and water present in this beaker. Even if you shake the beaker up, you close it, shake it, set it down, those two layers will always form. Water will hydrogen bond with other things that it can hydrogen bond with. Octane only has dispersion forces, it's nonpolar, it's not going to mix with the water. Another example that is often used is if you have like an Italian salad dressing that's usually made of an oil, like olive oil, and a vinegar. Oils are all pretty much completely nonpolar. And vinegar is polar, it can hydrogen bond. So those two liquids in salad dressing stay separate because they have different intermolecular forces between them. You can shake it up and pour some of the liquid out, and hopefully you'll get a good mixture of them. But when you set the bottle back down, they'll separate back into those two layers. Now, some substances, and I mentioned acetone as one of them, they have both polar and nonpolar regions, and they can dissolve polar and nonpolar substances. So acetone, let's draw the structure of acetone. You can see the particle picture at the bottom there. The gray spheres are carbon atoms. The center carbon atom has a double bond to oxygen. And then the terminal carbons at the end of the chain are bonded to 3 hydrogens. So just looking at this picture here, there are areas on octane that are nonpolar. That's this CH3 area and this CH3 area. So I'm highlighting with similar colors as the other image here, where you can see the nonpolar areas are the CH3 groups, but then the carbon to oxygen bond is polar. So this molecule has both a polar area and a nonpolar area. The bonding framework, those CH3 groups, are similar to a hydrocarbon. Carbon and hydrogens only, which is nonpolar. So acetone can mix with nonpolar substances like cyclohexane and octane. The polar carbon to oxygen group makes acetone miscible with other polar molecules through a polar CO group, miscible with other polar molecules like acetonitrile, for example. The polar oxygen atom also has lone pairs. So if there were another molecule with a hydrogen bonded to oxygen, nitrogen, or fluorine, it can interact with it through a hydrogen bonding interaction, intermolecular force there. So acetone, this is why it's such a good solvent. It is also nail polish remover. It dissolves nail polish as you're using that on a cotton ball or whatever you use. It's dissolving the nail polish. It is a really good solvent for that reason, and that's why we use it to clean glassware in the lab, because it can dissolve a lot of other substances. And then we just rinse it out. Okay, so let's look at this learning check. We'll give an explanation for the following trend in alcohol solubilities in water. So these are all alcohols. They all have a certain number of carbon atoms, but they all also have an OH group. So I'll just draw propanol here. It has 3 carbons and then the OH. So the OH area can hydrogen bond with water, but the other part of the molecule is nonpolar. So on the right, you can see that propanol, the molecule I just drew the Lewis structure for, is completely miscible with water. It'll always mix. But butanol, so if we take, I'm going to replace one of these hydrogens with a carbon. So now this is butanol, and this is just to demonstrate how these molecules change as you go down this table. Adding that extra carbon there reduces the solubility of that alcohol. It is only soluble up to a concentration of 1.1 molar. 1.1 moles of butanol per liter of solution. If you add any more after that concentration, it won't mix. And then if you go down and look at pentanol, we have an additional carbon. There are 5 carbons here that has an even lower solubility. And then hexanol has 6 carbons. That's an even lower solubility. As you go down this table, the substances increase in their nonpolar region, which makes the overall molecule less polar, which makes it less soluble in water. Or we can say as you go from bottom to the top of the table, Shorter hydrocarbon chain would result in a more polar substance. More polar the substance, more solubility it has in water. So let's write that down. Shorter hydrocarbon chain means there is a more polar molecule, or we'll say more polar substance which is more soluble in water. Because water is polar. And then again, this is a result of like dissolves like. More similar polarities in intermolecular forces, more miscible. Going to this next slide now, this is describing two different solids. So we had talked about covalent solids. Remember, these are like diamond or graphite or quartz. These are insoluble in all solvents, but they might react with specific liquids or vapors. That would be specific information. I don't think that's covered in this chapter. Molecular solids, so that is like ibuprofen, sugar, water. These conform to like dissolves like. They dissolve readily in solvents that have similar types of intermolecular forces. Example on the next slide is about glucose. So glucose is shown here. These numbers, by the way, should be subscripts, C6H12O6. And before we even fill in this blank, let's look down to the image here. I'm going to highlight the area that is glucose in yellow, because there's also some water molecules, so I want you to be able to visually see the glucose part. So that is the yellow highlight. That is glucose. There are multiple oxygen to hydrogen bonds, and this image is showing them hydrogen bonding with water. So this hydrogen bonding capability makes glucose highly soluble in water. Each OH group on glucose forms hydrogen bonds with water molecules. So as glucose dissolves, hydrogen bonds between water molecules are lost, but new hydrogen bonds are formed between glucose and water. So we can do more highlighting. Each water molecule I'll highlight in blue. Again, just so we can see it better. Pick out that information. And then hydrogen bonding interactions, I will use that orange color. So there are multiple locations where hydrogen bonding can occur. That is why sugar is soluble in water. Here's another learning check, thinking about the same thing. Vitamins are organic molecules that are required for proper function, but they're not synthesized by the human body. So vitamins must be present in the foods people eat, or they can be present in supplements. Vitamins fall into two categories. They can be fat soluble, which those vitamins dissolve in fatty hydrocarbon-like tissues, or they can be water soluble, which they dissolve in water. So the structures of several vitamins are below. We're going to assign each one to the appropriate category, fat soluble or water soluble. Okay, before we do that, I need to explain what these structures are. So let me go back to my blue color. Each time, I'm just going to look at vitamin E for now. Starting on the right side, anytime you see the end of a line, that is a carbon atom. So just drawing a couple in right now. And hydrogens. And then anytime there's a bend, that's also a carbon and hydrogens. So I'm not going to draw in every atom. We don't need to know every single atom. But what you need to recognize is that that whole chain that I just drew the carbons in for, again, all these carbons also have hydrogens bonded to them. That whole thing is nonpolar. Same with all of these. All of these are carbons and hydrogens. Now there's 2 oxygens present here, but most of this molecule is nonpolar, so it would interact with other nonpolar substances in the human body. This vitamin would be absorbed through fatty tissues. So this is a fat-soluble vitamin. Vitamin A, see the same thing. The only atom present that's not a carbon or hydrogen is this oxygen right there. Just one oxygen, and there are a lot more carbons and hydrogens present. This is a fat-soluble vitamin as well. Remember back to, I'm going to scroll up real quick to this learning check. We saw with larger number of hydrocarbon or larger hydrocarbon chain, the solubility decreased. If you continue increasing that hydrocarbon chain, that substance will now become more soluble in fatty tissues, nonpolar tissues, rather than water. So that's what we're seeing here. Vitamin A is also fat soluble. I'm just going to write, FS for fat soluble. Now, if we look at vitamin B5 and just pick out atoms that are different than carbon and hydrogen, we have oxygen, oxygen, nitrogen, oxygen, oxygen, oxygen. So although there are a number of carbons here, there are also a good number of polar bonds, atoms that can hydrogen bond, atoms with lone pairs. This is a more polar molecule, so this would be water soluble. So I'll write WS here for water soluble. We can see the very similar for vitamin B6. A number of hydrogen bonding capable areas. This is also water soluble. Before I go through these last two, you might just pause and try to figure out if they are fat soluble or water soluble based on their structures. But if we look at vitamin C, again, we have a number of oxygens that have hydrogen bonding capabilities. This would be water soluble. Vitamin D is, we've got one oxygen atom here, a whole bunch of carbons and hydrogens. This would be fat soluble. I actually have a vitamin D supplement that comes in a dropper. The vitamin D is dissolved in olive oil. Oils are mostly nonpolar. So the vitamin D is dissolved in that, and then I can drop that. And that's how I get vitamin D in the winter. Okay, so let's talk about the solubility of metals. So previously, these are molecular solids, right? Each of them are molecules. Now we're looking for solubility or describing solubility of metals. Metals don't dissolve in water. This is good. You've got a silver or gold ring on. Definitely don't want that dissolving when you wash your hands. Metals contain delocalized bonding networks that have to be disrupted before the metal can dissolve. Water can't disrupt that. We're talking about metallic solids, by the way, so that's mostly transition metals. There are some metals that will react with water. We learned about that last term, but think about transition metals here. Metals also don't dissolve in nonpolar liquid solvents. So water is polar, metallic solids don't dissolve in water. They also don't dissolve in nonpolar liquid solvents, but they can dissolve in each other. And that's how we get an alloy. So alloys are a mixture of substances with metallic properties. They occur when metals dissolve in each other. They can be homogeneous or heterogeneous. They can be substitutional or interstitial. Sterling silver is an example of a substitutional alloy. If you look at the way these atoms are arranged, the copper has substituted for a location where silver could be. So a silver could be right there, but the copper has taken that place. So it's substituted. The other type is interstitial. Here, this is carbon steel, which is made of iron and carbon. These larger spheres are all iron, and then you can see carbon is sandwiched in between those spaces, or within the spaces in between iron atoms. So that would be an interstitial. So those are different types of alloys. This is a solution. Looks uniform. If you look at that knife at the bottom there, it looks uniform. Another example would be like if someone has a gold tooth, a metal tooth, those are made of alloys. There are lots of different types of alloys out there. Like cookware. I don't know. There's a big list. You're welcome to look up different types of alloys. A specific metal mixture that occurs with mercury is an amalgam. So mercury, this is element 80. This is the only metal that's a liquid at room temperature. It dissolves a number of metals to give liquid solutions, and those liquid solutions are called amalgams. So an amalgam is any solution of another metal dissolved in mercury. Metals that are close to mercury on the periodic table, like silver, gold, zinc, tin, these are all particularly soluble in mercury, just to give you some examples. Okay, so let's talk, we're going to move into a little bit of the energetics of something dissolving. So the solubility of salts, now we've talked about this many times, we're going to go through it again. Many ionic solids dissolve in water. Water is highly polar, but it's not ionic. So to dissolve, the interactions between ions and the solvent must be strong and overcome the attractive interionic forces of the crystal lattice. Okay, so cations and anions are solvated. This is that process of becoming dissolved by strong ion dipole interactions with water molecules. So this, I think, is actually the same or very similar image that's on the bottom here when we introduced intermolecular forces, describing ion dipole forces. This happens when an ionic solid dissolves in water, because the ionic solid separates or dissolves into the cation, which is shown in green, and the anion, which is shown in red here. In water, molecules have ion dipole attractions. So those are these arrows here. That's that force of attraction between water and the ion. So in order for an ionic solid to dissolve, that ion dipole interaction must be stronger than the attractive ionic forces of the crystal lattice, which are shown here. All of these interactions there. I think we'll end here. Well, actually, I know we'll end here. We'll continue talking about this. I'll review this slide again and then talk about solubility, equilibrium, and energetics, and so on when we get back to class on Monday. So I hope y'all have a good weekend, and I will see you then.